Hello, everybody. I hope you are studying calculus and you are getting ready for test number 4 in this course, Math 213. All right, so this video is going to cover practice test number 4, and you have practice test 4 as well as its solutions in the module for test 4. And so I'll be going over those problems just like I did for the integral review. And so let's get started. I'll be sharing my screen with you again. All right, so as you know, you've had the review of triple integrals at the end of chapter 5, and now we're going to practice test number 4. If you click on this, you'll realize that practice test 4 has 12 problems, and this practice test, it says at the very beginning, sections 5.1 through 5.6, and you may wonder, well, what about this one, 5.7? Okay, so I just want to tell you. 5.7, change of variables, that's the section on Jacobians and UV substitution. I am not going to ask you any questions from section 7, all right? So don't worry about section 7. You should do your homework on section 7 because I do want you to know how to find the Jacobian, how to calculate, translate from XY to UV and so on. And that is a meaningful and good technique to learn. However, for this test number 4, this is not the main topic, and in order to focus on what's important, I will not be asking you questions from section 7. All right, so I hope you will try, and you have maybe you have answered or tried to answer the questions from practice test number 4. I will be sharing a screen so that you can see the problems as well as the answer key. All right, let's get started. Okay, so as I said, practice test 4, this covers the first 6 sections only, all right? That's only, but that's a lot of work, right? So try to, review your double and triple integrals, not just the integration itself, but how you visualize, how you sketch, how you interpret these integrals, and not in the rectangular coordinates only, but also in polar, cylindrical, and spherical coordinates. All right, number 1, evaluate this integral. I hope this is going to be simple. Let's go ahead and look at the solution. And I will be making notation with my green pen, green virtual pen, right? So multiple integration. So how do you integrate this with respect to x? Well, if x goes from 0 to 3, this just becomes 3 cosine of y. Right? Don't do anything fancy. You don't have to do a whole lot here. All of these are constants, which means it should be a very simple, straightforward integration problem. And so 3 cosine y becomes 3 sine y. And if you integrate 3 cosine y, it becomes 3 sine y, going from 0 to pi over 6. Sine of pi over 6 is 1/2. Sine of 0 is 0. This is 3/2. No problem here, right? Okay, look at number 2. Let D be the triangular region on the plane with vertices 0, 0. Now, if you are asked to evaluate this kind of integral where the region is described in, basically the English language, you should try to sketch the picture of the domain, right? So the region that you are thinking about or they're asking you about is a triangular region with the vertices 0, 0 and 0, 2 and 4, 2. 1, 2, 3, 4. Okay, so think about this region. Okay, and in fact, if I were you, I would quickly draw a picture of this so that I can clearly visualize what I'm doing. Okay, then evaluate this integral. The order of integration is relevant here. All right, so dA, and of course this is d. What's dA? Well, usually it's dy dx. Sometimes it's dx dy. And it seems like, if you look at this thing here, e to the y squared, that looks like a pretty difficult function to integrate. Okay, and in fact, you probably never integrated e to the y squared. There's a reason for it. You can't. Okay, there's no easy function of y whose derivative is e to the y squared. Right? So this is not an the derivative of any simple function. And so you probably do not want to do dy dx, because the first step should not be to try to find the antiderivative of this function, which does not exist as a simple function. Maybe as an infinite series or something. But okay, so maybe you can focus on dx dy, right? So that tells me, by the way, and I'll show you the solution in a few minutes. But that tells me I have to describe this area D, or the region D, in this order: dx dy. Y goes from what to what? Okay, 0 to 2. And then for each y, x goes from what to what? X goes from 0 to until you hit this line, right? And that require, and by the way, your mind should be thinking, all right, so what's this endpoint? This equation is y is 1/2 x plus 0. How do I know this? Well, that's something you learned in your first algebra class when you were 3 years old, right? So the slope is 1/2. I hope you can see that. 2 divided by 4. And then the y-intercept is 0. So this is the equation. But you also learn that in a situation like this, where the d, if you have to describe this as a dx dy type of region, otherwise known as a horizontally simple region, you have to solve this equation for x. So x is equal to 2y, right? So this is something that you should write down before you even think about integrating. Okay, so here's the solution, and I have a picture of this, of course, and I make a little note here: e to the y square is not what we call an elementary function. There is no antiderivative. So then I do dx dy, as I just mentioned. Would it really help? Well, sometimes it does, sometimes it doesn't. This time, of course, since this is a problem on your practice test, it will work out, so that if you switch the order of integration to dx dy, it actually works out. And the reason it works out is because you have a y in here. If this was a constant, in the rectangular region, you will not be able to do this. But let's go ahead and try this. Once you try to integrate this with respect to x, of course, you have 2y minus 0, which is just 2y, comes in front of it. Now you see this y really helps you out, because you can now you can use u substitution. Let u be y squared, okay? And so du is, of course, 2y dy, and that's exactly what you see here, 2y dy. How nice. This will be e to the u du. And of course, these numbers also change, right? So u, when y is equal to 0, u is 0. When I made a mistake here. When y is 2, then u is y squared. So u should go from 0 to 4. Okay, and that's what I have here. So this whole thing becomes a very simple expression: the integral from 0 to 4 of e to the u du, which is e to the u, where you plug in 4 and 0. And so that's e to the 4th minus e to the 0th, which is e to the 4th minus 1. All right, let's look at number 3. By the way, you notice here, if you try to do this in the order dy dx, you get stuck in the very first step. Okay, so sometimes it's required that you switch the order of integration. Number 3, switch the order of integration for the double integral below. Do not evaluate. I have a little suggestion for you. If I say do not evaluate on your exam, please do not evaluate. Your time is very precious. And the reason I say do not evaluate is probably because it becomes really, really messy. Okay. All right. So right now it's dy dx. Oh yeah, by the way, this one you cannot evaluate even if you wanted to, because I didn't tell you what f of xy is. All right. If you switch this, how do I do that? Look at this. You can't do this problem unless you know what the region looks like. Okay. So x goes from 0 to 3. I'm thinking, here, 0 to 3, right? And then y goes from x squared. Y is equal to x squared. Well, yeah, I know what that thing looks like. It looks like this, right? And it goes up to 9. So you know y is equal square goes through the point 39. So this is very appropriate. And y goes from x squared to 9. So where is that? If y goes from x squared to 9, I hope you know it's this part and not this part here. Okay? This is not the part you're thinking about. If it's this region, y would be written as from 0 to x squared. But that's not what's written here, right? It's x squared to 9. So it's this part. And now you think of this part, right now, this is a vertically simple region, but instead, I am going to start thinking as a horizontally simple region. And so you would be expected to solve this for, x. Okay, let's take a look. So number 3, so this is a picture I drew. And so the question now is, in order to write this as dx dy, I have to ask myself a question first. Y goes from what to what? That's easy, from 0 to 9. So that's what this is. And then x goes from this point to this point, this point to this point. For each y I value, for each point I pick between 0 and 9, x goes from whatever this point is all the way to when you hit this parabola, right? So, and of course, the lower limit is 0. The upper limit is when you hit this equation, y is equal to x squared. But of course, you have to write this in terms of x. So x is the square root of y. It's not positive or negative because we don't have to worry about this part. Okay, so the answer is x goes from 0 to the square root of y. And this is the answer to the question. Okay, number 4, evaluate this integral, showing each step. Again, if you try to do this, I hope you don't say the integral is the cosine or negative cosine of y cubed over 3. That's not the way it works, right? Because this is a composition of two functions. You have a sine function and the y square function. Do you know a function whose integral or whose derivative is sine of y squared? You don't, okay? Because we don't have a function, a simple function whose derivative is sine of y squared. So as soon as you notice that, you say, you know what, something is messed up on this problem. I really shouldn't be integrating this with respect to y, at least first. So maybe I should switch the order of this, okay? Now, the problem may not say that, but that's the only way that you can do this problem if you switch dy dx to dx dy. So think of switching to dx dy because that would be the only way to evaluate this. Possibly, maybe you still can't, but you probably could because this is a problem on the practice test. All right, so instead of having these numbers, you'll have to switch, okay? And before you switch the order though, you have to know what the thing looks like. Okay, so x goes from 0 to pi, a square root of pi, right? I don't know what that number is, okay? It's less than 3. Okay, and then y goes from x to the square root of pi. So what's y equals x? That's this line, right? So y goes from this to the square root of pi. So it's going to be this part. That's the region that I should be thinking about. And I should be thinking about this now as a horizontally simple region. So y goes from 0 to square root of pi, and then x goes from 0 to, and again, I will be asking this question, 0 to what? And the answer is, well, x has to be equal to y. So that's a kind of, process that you would have to take at the beginning of this, even before you start to integrate. All right, so this is the solution sheet or the solution, the answer key. I drew that picture, all right, and then remember, so first you recognize that this is not a possible thing to integrate. And so you switch the order, and in this case, y goes from 0 to pi, square root of pi. And then remember, for each y, x goes from this point to wherever it hits that line, which was y is equal to x, but now you write it as x is equal to y. So x goes from 0 to y for each y you pick. And after that, you integrate as y goes from 0 to the square root of pi. So how does it help? Well, if you integrate this with respect to x, this is basically a constant. So you just get y minus 0, which is y, okay? And just like before, you should be very thankful that you have this y, because now I can use u substitution. Let y squared be equal to u, and then du is 2y dy, which you don't see, but of course, if you really wish there was a 2 in front, you just wish upon the star, and it suddenly appears. And if nobody's looking, maybe you can just sneak in this number 2. Now you can't, right? Because you have to make the little compensation. If you multiply the inside by 2, you'd better divide this thing by 2, and that's why this 1/2 appears in front. And then, of course, when y is equal to 0, u is also equal to 0. But when y is equal to the square root of pi, remember, y squared is what u is, so you have to square that. And if you square the square root of pi, you just get pi. It's funny to think if you square anything, you'll get a piece of pi, but that's what happens here, right? Okay, so the new integral is going to be 1/2 of the integral from 0 to pi now, right? And then sine u du. This is very simple. The antiderivative of sine of u is negative cosine of u. And you have to be careful with the cosine, because cosine doesn't behave as nicely. Cosine of pi is -1, and cosine of 0 is 1. And you have to subtract -1 minus 1. That's -2. And you have -1/2 in front. So the answer is +1. Okay. Let's go to number 5. Convert the following into polar coordinates and evaluate. All right. So again, you should draw a picture of this. What happened to my red here? X goes from 0 to 2. Okay. And by the way I'm drawing this is exactly what I would do if I were you. If I were taking this as a test or something. As soon as I see this and this, I draw this. And then y goes from 0 to square root of 4 minus x squared. Oh, I should mention here, I'm writing a bunch of things here, but this is not how I would write on my work. If I have to show my work, it's okay to write this kind of thing as a scratch paper, but when you're formally trying to solve these problems, you actually do have to write more formally like this. Okay, this will be okay. But again, as soon as I see this, I would be drawing a picture like this, and then I would be squaring this. And you say, oh yeah, that's x squared plus y squared is equal to 4. And that's the circle. But since x only goes from 0 to 4, and of course, y only goes from 0 to this, so it has to be just this region. All right. And of course, what do I have to do with this? X and y are not in the language of polar, right? Polar coordinates don't have x and y, but it does have x squared plus y squared. Okay, that's a long word, x squared plus y squared, if you are living in rectangular coordinates world. But in polar, this is really simply r squared, right? So with that in mind, you draw this and you realize this is just r squared. So you basically have r cubed, because dy dx becomes r dr d theta, right? So this is dA, this is dA in their respective coordinate system. And so r cubed is what you have to integrate, because that's what you see. And so that becomes 1/4 r squared to the 4th. Plug in 2 and 0, you just get 1 for this. And so then actually you get 4. Sorry, 2 to the 4th is not 4. 2 to the 4th is 16. So 16 over 4 is 4. And then you have pi over 2. So the answer is 2 pi. All right, we have 12 problems in this entire thing. Let's do one more, and we will take a break and go to the second part of this video. Find the mass of a solid bowl. Okay, so remember mass? Mass is basically a triple integral with the density function as the integrand. Okay, so that's not really difficult. And especially, the way I try to teach you that integration is a continuous version of addition. So if you think of this solid bowl as this, and every point has a different density, I hope you understand that the triple integral of the density function is the total mass of this solid. Okay, so it's bounded by z is equal to x squared plus y squared. That's, this kind of thing here. And z is equal to 1. So you cap it at this point and or this horizontal plane and assume that the density for each point is given as z. All right. So think about this kind of a bowl. If you look at this from the top, it just becomes a unit circle. So hopefully, by the way, you have already decided to use polar or cylindrical coordinates because things are round and rectangular coordinates don't go well with something round. Okay, you can't um, you can square a circle, as they say. All right, so theta goes from 0 to 2 pi. R goes from 0 to 1. That's easy because of this. And then Z, that's easy too. If you are thinking of this bowl here, okay, then the bottom number is not 0. So in other words, this number is not 0. In other words, I'm saying it doesn't go from 0 to R square. And by the way, R square is here because Z was given as x squared plus y squared, which of course we know as r squared. So z does not go from 0 to r squared because that would be from here to here. That would be the outside of the bowl. If you're looking for the volume of the bowl, then the bottom number, the lower limit of z should be r squared, and it goes up to 1, right? So that's what this is. The integration is a simpler part of this calculation, the problem, I think. If you integrate z with respect to z, you get 1/2 z squared. You plug in 1 and r squared here. And remember, you still have that extra r waiting to be processed at the end. So I would take the 1/2 out. I always try to take the constants out first. And then you have 1 squared minus r squared squared. So that's 1 minus 4 r to the 4th. And then you have an extra r here. Where did that come from? It came from the a in polar coordinates. So this is r minus r to the 5th. That's what you're integrating with respect to r. And that's 1/2 r squared minus 1/6 times r to the 6th. That looks terrible, but fortunately the numbers are 0 and 1, so it's easy. It's 1/2 minus 1/6, and that is 1/3. Okay, so this part is 1/3, and you have 1/2 here. And then you have 2 pi coming from here. 2 and 2 cancel. The answer is pi over 3. Okay. Now, the volume of this thing is not pi over 3. The volume of this bowl is bigger than pi over 3. But the reason this is pi over 3 is because you actually integrated this. Remember, this is not the volume. This is what we found is the mass. And the mass had this extra z in there as the density function. And so that's why the volume is bigger than pi over 3. Because pi over 3 actually would be the volume of this cone, right? So this bowl is bigger than that, okay? But the mass is pi over 3 because of the density function. Okay, so that's the first 6 problems. Let's go to the next video for the part starting in problem 7.